Number 18 asks us to draw the major product of this reaction sequence. Now this is a question that's based on material from the second exam involving malonic ester syntheses. So the first step you're given is, well, you're given a diester, a malonic ester more specifically, and then an OET. An OET minus we've seen is either a base or a nucleophile depending on the settings. Now, if you have a base and you have an ester, and that ester's OR group is the same as the OR group over the arrow, you're not attacking the carbonyl. Because technically, while this could attack the carbonyl and this swings up, you just end up kicking out an OET group again, and then no change would occur. So what this OET has to do eventually is pull off a proton. So that OET minus comes in, grabs that proton, and you form an enolate. You have O minus, OET, and double on there. Now, you could form the enolate with either carbonyl because this is symmetric. Neither side is better than the other. I just chose the left side arbitrarily. And so this will be the product of the first arrow. The second arrow involves a benzene ring with a bromine on it. And we know bromine is a good leaving group, which means the carbon it's attached to is generally going to be attacked by something. Who is going to do the attack? Your enolate. Now remember, enolates have a resonance structure, where this swings down and this goes to that carbon, which means your resonance structure puts a negative charge on this carbon over here, meaning it would look like OET, carbon minus, like this. So if you're ever confused which carbon does the attack for an enolate, it's always the alpha carbon, the carbon that's a single bond away from the carbon with the oxygen. So this one over here, the carbon that doesn't have the oxygen, in other words. So you can either draw the resonance structure like this and then have this negative charge attack there, or you can just draw it from the enolate attacking directly. So this O minus swings down, and then the double bond goes out and attacks. Either of these two arrows is acceptable, but make sure if you're using this one, you draw the resonance structure first. Either way, let's go with the top one, because this is the one we're going to be working with more often than not. So the enolate swings down, the double bond goes out and attacks the carbon with the leaving group on it, and then the leaving group gets kicked out. And so now you have two esters. And now you have, let's see, 1, 2, a carbon and then the benzene. So 1, 2, a carbon, then the benzene. Okay. So that is the product after the second arrow. Now the third arrow, OH minus, H3O positive, and heat. What does that do? Now, I'm going to go through these steps individually because more often than not, people see this and say, oh, it's decarboxylation. But they forget the important why it's 3 steps. What is the purpose of the OH minus and the H3O positive? What if we gave you OH minus H3O positive, but didn't give you the heat? So, because heat is what actually makes the decarboxylation happen. So let's just look at that step 1, step 2 part first. OH minus, H3O positive, step 2. What this reaction does is it turns an ester into a carboxylic acid, meaning this OH minus comes in and attacks the carbonyl. The carbonyl swings up, swings back down, and kicks out either the OET or the OH. But because we're reacting with OH minus, we have a lot of extra OH minus than floating around, which means it's more likely to stay eventually. It's just a matter of, if we have 1,000 OH minuses and only a couple of these molecules, just by probability, you have a lot more OH that could attack and stick around, and if it gets attacked again, the OH gets kicked out, but you already have an OH there. Or you have another OH there anyway. Now, I'm rambling with that. Basically, it's the difference between using an O group that is the same as your OR group on the ester and an OR group or OH group that isn't the same. Whatever's over that arrow will replace your OR group. And in this case, it's OH minus. So you'd end up getting 2 carboxylic acids after those first 2 steps. So you'd have that and a very ugly drawn benzene. Now, one important point to make is what's the purpose of H3O positive? Because OH minus should do that on its own, right? Well, remember what a carboxylic acid is. It's an acid. It's a very strong acid. And if you have OH minus, a good base floating around, it's very inclined to end up deprotonating those OHs. So the reason why there's usually a step 2 H3O positive is just to ensure that these O minuses are protonated at the end until you fully have the carboxylic acid. And now we bring in heat. Heat is the actual thing that causes decarboxylation, not the 3 steps, although they're usually used in tandem with each other. You need 2 things for decarboxylation, or 3 things actually. A carboxylic acid, a beta carbonyl to that carboxylic acid, meaning if I number the carboxylic acid carbons 1, and then 2 on 3, there has to be another C double bond O, which there is in this case. Now all you need is heat. So you need a carbonyl that is beta to your carboxylic acid, you need a carboxylic acid, and you need heat. Once you have those 3 things together, decarboxylation occurs. And the way you decarboxylate is you chop off one of those carboxylic acids. So I'm breaking the bond between 1 and 2, but you could choose the bond between 2 and 3. But you only choose 1 because you always need a beta carbonyl. If I chop this off and this is gone now, after I use the heat, this no longer has a beta carbonyl to it, so I can't chop any more off. So this right here is your final answer. So just to reiterate what happens in decarboxylation, you find your carboxylic acid and it has to have a beta carbonyl. If there are 2 carboxylic acids, it doesn't matter which one you choose, but if this was just a carbonyl, you have to choose the carboxylic acid. And now you number 1, 2, 3, and you split the bond between 1 and 2. And so that bond is now gone. The carboxylic acid comes off as CO2, and that leaves you with a final product of this, which looks like carboxylic acid, 2 carbons, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, and then the benzene. So this was your final answer, and that was structure D, or choice D on the answer key. Okay? So the trick to this question that caught a lot of people off guard was when they saw this, they always thought decarboxylation, but they forgot the purpose of the OH and the H3O positive, to turn the esters into carboxylic acid. So always remember that's what it's for.